Hi, my name's Adam Ehal, and I'm here to welcome you to the first episode of Science, Learning the Hard Way. This series is about some of the magic, mystery, and murder surrounding the greatest achievements in science. So why are we doing this? Well, science gets a bad rap. It's not all number crunching and lab coats. I've learned way too much cool shit about our universe to keep it to myself. Before we get into it, we need to cover some basics. So follow me to one of my favorite places on campus, then we'll get into it. The Big Bang is widely accepted as the theory that explains the origin of the universe. Now, before the Big Bang, there was nothing. No space, no time, and no gravity. Everything was packed into one single point of energy. Now, this energy was released in an ever-expanding shock wave that we call the universe. So what happened to that energy? Well, in a way, you're looking at it. Come on, I'll show you. What you have to realize is that energy and mass are really equivalent. Following Einstein's equation E equals mc squared, energy can be converted into mass, and mass can be converted into energy. So what this really means is that in this early universe, it's hot, but it's expanding. So as space expands, it allows this energy to cool and be converted into mass. What we know now as hydrogen and helium, the two most abundant elements in the universe, were created in this early universe. So as gravitational effects took force, these elements swirled together into gaseous bodies that we know as stars. So you could really say, if the Big Bang gave the potential for existence, stars gave the potential for life. Massive stars use a combination of strong gravity and high temperatures to accomplish nuclear fusion. Hydrogen atoms fuse to form helium, helium and hydrogen fuse to form lithium, and so on, forming all the elements you are familiar with on the periodic table. The fusion of lighter elements releases enough energy to power the star for its lifetime. The elements within a star will continue to fuse until they form iron. Fusion of elements to form atoms heavier than iron will no longer produce energy. Rather, it will require energy input. This energy is readily available once a star has exhausted its lighter element fusible fuel. This depletion of energy producing fusion will eventually result in a cataclysmic event called a supernova. Basically, the star explodes, and the immediate moments following provide enough heat and energy to fuse heavier elements than iron, which are consequently blasted off into space. Great. So now we know how the elements were formed and why the lighter elements are more abundant in the universe. So now let's take a look at the atomic structure. We have protons and neutrons in the nucleus with electrons surrounding it. Now the stability of an atom can best be explained by an analogy. Imagine these protons as little positive magnets. The closer they get, the larger the repulsion. Okay. Imagine uranium. Atomic number 92. This means that it has 92 protons in its nucleus. So imagine 92 positive charges exerting repulsive forces on each other. Well, that's not all that's going on. Scientists have discovered that the neutron, aptly named, is sort of a mediator in this proton battle. It gets in the way and it lessens the intensity of these repulsive forces. So it takes more than just these protons to fuse together to make a stable element. You also need the appropriate number of neutrons. Radioactivity describes these nuclei that are unstable, meaning at any moment that this nuclei may kick out these protons, and because it's striving for stability, really, it wants to turn into something more stable, and it'll achieve that if it kicks these protons out. But it's not a nice, friendly, all right, go next door, proton. It's a violent, angry departure. So who cares if this is happening in deep space? Well, this is where it gets interesting. Much in the same way that a massive star forms heavy elements, the energy released in a nuclear explosion is enough to form a variety of stable and unstable elements. For this discussion, we're concerned with the nuclear fusion byproduct strontium-90. It's Nevada, 1951. The government begins nuclear weapons testing over the desert. They believe this to be a localized hazard, something that would remain in the desert. In St. Louis, a scientist was doing studies on the composition of children's teeth.
Children are a good monitor of calcium and strontium uptake because they're constantly growing, forming new teeth, losing their baby teeth. He found that there was an unusual amount of strontium-90 in their teeth. Now this could only be explained as being cause of these nuclear weapons testings. Well, the thing about strontium-90 is it's very radioactive. And when you have a radioactive material, something that's going to decompose, it's going to release a lot of energy. Something near a biological system, that's going to maybe disrepair DNA, something that would cause cancer, very damaging stuff. The same year that the scientists' studies were published, the US signed a treaty to ban atmospheric weapons testing. Now that's what I call learning the hard way. Join us next time. Give us some submissions or we're going to pick the topic. Thanks.